So in the last session, we have discussed an introduction to large language models. We also discussed what is prompt engineering. Now that is at a very superficial level. If we already have a large language model in place, how do we really use it? Like a user point of view, not really a developer point of view or a data scientist point of view. As a user of a large language model, how do you use large language model effectively? Now, to understand large language models, if you talk about Chat GPT, T stands for transformer. So all these large language models are transformer based architectures. These are all transformers. Now, what is a transformer? To understand what exactly is a transformer, we need to understand what is encoding and decoding. In transformer, there is something like encoders, there are something like decoders. To understand encoder-decoder architecture, we may have to understand what is sequential data analysis using LSTM, long short-term memory. Now, long short-term memory is an advanced version of something called recurrent neural networks. Recurrent neural network is one of the deep neural network algorithm. Deep neural network is a specialization of artificial neural network. Artificial neural network can be understood if you look at something called logistic regression. Layered logistic regression is artificial neural network. To understand logistic regression, we have to understand linear regression. So to reach a large language model, this is the path that we have to follow. So today we're going to discuss linear regression and logistic regression. Later on, we'll go to artificial neural network, deep neural network, recurrent neural network. But this is all like very dense theory. We will just have an overview of it, but mostly we will focus on the transformer applications and using them. Otherwise, we'll just go through that architecture once and then we'll wrap it. But at the end, once again, we will revisit this and go through the theory once again. So that is the idea. Today, our focus will be around linear regression and logistic regression. These are some of the most important machine learning algorithms. The reason is if you understand this, maybe you will have a good idea to follow rest of the algorithms that are coming up. Let's go to the details of linear regression and logistic regression. If we talk about correlation, let us suppose if we have two features, is there any association between hours of study and the final marks somebody gets? Hours of study and final marks. Is there any association? Maybe some people will say yes, there is some association. Our final marks depend on how many hours we are studying. Some people may say that there is not such association. Is there any association between temperature and sweater sales? What about this one? Temperature versus sweater sales. Is there any association between these two?
Yes, sir.
Here there is definitely an association. As the temperature increases, as it gets hotter and hotter, what happens to sweater sales? Sweater sales goes down, decreases. As the temperature decreases, as it gets colder and colder, sweater sales goes up. So definitely if you look at temperature versus sweater sales, definitely there is an association. Like that, if you take any variable, temperature versus ice cream sales, whenever we are thinking like this, variable X versus variable Y, let's say variable X is hours of study versus variable Y, final marks somebody is getting. Is there any association between them? If I want to know, is there really any association between them? How do I really find out? You have to gather the data. Maybe take around 1,000 students or 2,000 students. Look at on an average how many hours they are studying. Maybe weekly average hours of study. For all the 1,000 students, weekly average hours of study. For all the 1,000 students, what are the corresponding marks? For all the 1,000 students, what are the corresponding marks? Now, once you have this data ready, you can use a statistical metric or you can use a statistical measure called correlation coefficient. Correlation coefficient. What this correlation coefficient does is it will try to quantify how strong, how weak two variables are associated with each other. Correlation coefficient formula is covariance of xy divided by variance of x into variance of y under the root. Covariance of xy tells us what is the together variance. That means if x is moving a lot from its mean, is y also really moving a lot from its mean? If x is deviating minimal amount from its mean, y is also deviating minimal amount. Whatever is happening to x, if y is moving in synchrony, then covariance will be high. Whatever is happening to x, y has no connection to it. If x is moving a lot, y has no connection to it. If x is moving a little bit, y has no connection to it. Then covariance will be a smaller value. So in the numerator, we have covariance of xy, together variance. In the denominator, we have variance of x into variance of y under the square root. This is the correlation coefficient formula. If the correlation coefficient value is 0 to 0.25, negligible association, 0.25 to 0.5, weak association, 0.5 to 0.75, moderate association, 0.75 to 1, strong positive association. And in scenarios like this, where one variable is increasing, the other variable is decreasing. If x is increasing, y is increasing, correlation will be positive. But there is other type of relation as x increases. For example, in our example, temperature as it is increasing, y is decreasing. That means our sweater sales was decreasing. In this case, correlation will be negative. So correlation is negative also because the relationship between two variables not necessarily always directly proportional. Inverse proportional relationship is possible. If the correlation is between 0 to minus 0.25, it is negligible negative. Minus 0.2 minus 5, weak. Minus 0.5 to minus 75, 0.75, it is moderate. Minus 0.75 to minus 1 is strong negative. So correlation varies between minus 1 to plus 1. If it is near to plus 1, it is near to minus 1, very strong correlation. If it is near to 0, that means there is not much of correlation or negligible correlation. So in short, given any two variables, if you want to find whether they are associated with each other or not, you can use correlation coefficient. That's the theory behind correlation. Let us try to do one quick case study, find the correlation and see how to write the code for it and how to analyze the output. Before I get there, any quick questions on correlation, anybody? For example, if I give correlation between x and y is 0.2, correlation between x and z is minus 0.8. So which correlation is higher?
Minus 0.8.
Minus 0.8.
So numerically 0.2 may look higher than minus 0.8, but from the meaning, from the correlation point of view, minus 0.8, it indicates that very strong negative association versus 0.2, which is a negligible positive association. Always this is much higher. Let us go to our code file. Before that, let me introduce this particular data set to you. This data set is 8 passengers data. In this data set, we have several columns. This particular data set has been shared by one airline company. The objective here is this airline company want to study what are the trends, what are the factors that are impacting the number of passengers. What this company has observed is there are some weeks the number of passengers are very high. On certain weeks, the number of passengers are very low. Yes, there are few weeks where passengers are low. There are few weeks where passengers are high. What I want to do is, what are the most influencing factors? Why passengers are high here? Why passengers are low here? What are the influencing factors that are influencing the number of passengers? Why in some weeks passengers are high? That is what are the drivers that are impacting it? That is what we want to study. So the data that we have, so this airline company has gathered around 80 weeks data, almost like nearly 1.5 years data they have gathered, and we have the access to that data now. 80 weeks data, we have week number, we have number of passengers who took the flights during that particular week. We have the promotional budget in that week, the amount of money that is spent on promotions, offers, coupons, marketing. So promotional budget. Isn't it true? Promotional budget impacts our number of passengers. If you are giving more and more offers, there's a high chance that passengers may increase.
Yes, sir.
Yes, sir.
Yes. Promotional budget impacts passengers. Service quality score versus passengers. Holiday week versus non-holiday week. Does it impact passengers? Delays, cancellations from our side. Does it impact the passengers? Inter-metro flight ratio. There are flights between metro to metro cities. There are flights between metro to non-metro cities. Does it impact the passengers? Bad weather versus good weather. Does it impact the passengers? Technical issues. We have some technical issues, ticketing issue or website not working, some technical issues from our side. Does it really impact the passengers? So maybe all of them may impact, some of them may not impact. I want to know what is the driver that is impacting the passengers. So the first question that I have is passengers versus promotional budget. Is there any association between passengers and promotional budget? If we have to answer that question statistically using statistical measures, what will be the measure that we will be using to check whether two variables are associated or not?
Correlation coefficient.
We have to use correlation coefficient. So we will use the correlation coefficient. If the correlation coefficient value comes to be a higher number, then we will say yes, passengers and promotional budget are related to each other. I'm going to pass on this PPT as well as the code files along with the video. Right now, let me give you the location of the code file so that you can access it. Let me give you the code file link right now.
Venkat sir, I would like to add here something.
Yeah.
So we are going through linear correlation, right? These are all linear correlation. Formula is linear.
Right.
So there's also when data is non-linear.
Mm.
So I think you can talk about that also. That would help everyone. And how the correlation is mainly different from the regression. So the my takeaway from all years of experience in ML, in very layman language, correlation is a two-directional thing, and linear or regression are the unique one-directional thing. Causal, if you don't want to name causal, then it's like a one-directional x. We would like to find y, which is dependent on x. But x, we can't find x dependent on y. But in correlation, we can if both are associated. You bidirectional thing is correlation. We just want to add these two things.
Yeah. Actually, in the participants, some of the people are from absolute beginner background. So I'll go
Okay.
one by one, like from absolute basics, I'll try to add on delta by delta, delta by delta. Otherwise,
Yeah.
too many things if we discuss, that will be kind of overwhelming and hard to catch up. Okay.
Yeah.
One by one, depending on the situation, along with the cases, I'll
Yeah.
add them.
Sure.
Okay.
Sure.
Yeah. So there's a code file that I have pasted in the chat window. What I want you to do right now is do not execute a lot of code. Usually it is a good idea to write the code, but in the interest of time, we may not get that much time to write it in the classroom, but it's always a good idea to practice it or write it when you're going through this video. So import the packages, import the data set. The data set is air passengers data. And to find the correlation coefficient, the code that we have to write is np.correlation coefficient, np.core-coefficient, mention variable 1, variable 2, you will be able to find the correlation value. Once you have the output of this, give me a confirmation. I'll explain how to read the output of that correlation coefficient code.
So the output which we are getting here, is it very similar to the heat map matrix?
Yes, we can create a heat map out of that. So the output that you get here, let's say you are asking the output for, like we want to find the correlation between passengers and promotional budget. So the output will be a matrix.
Yeah.
In this matrix, you have passengers and promotional budget. So there are 4 values in your output. The first number over here indicates the correlation between passengers and passengers. Obviously, if you take variable X and try to find the correlation of that variable with itself, that will be 1, isn't it? Correlation between any variable with itself will be 1. Similarly, if I come to this element over here, correlation between promotional budget and promotional budget, that will also be 1. Doesn't matter. That's not the correlation that we are looking for. We're looking for this number, correlation between passengers and promotional budget. How much is the correlation between passengers and promotional budget? How much is the correlation between passengers and promotional budget?
0.96.
0.9658 something. Now, if you come here, this is the correlation between promotional budget and passengers. In reality, it will be same as this one, because if you go back to the correlation formula, if I say correlation between X and Y or Y and X, if I say X into Y or Y into X, it will be same. So correlation between XY will be same as YX. The correlation between promotional budget and passengers is 0.9658. So in one word, if you have to give me the answer, what is the correlation between passengers and promotional budget? What will be that number? How much will be the final number? What's the correlation value? 0.9658. Imagine I'm a layman. I don't understand what exactly this 0.9658 mean. What exactly it means?
Strong correlation.
There is a strong, no, strong negative is there, strong positive is there. We need to be a little specific, because correlation can be negative also. There is a strong positive association or strong positive correlation between passengers and promotional budget. Now we will go back to our client or the business partner. We start explaining them that I have done some analysis. In this analysis, I found that there's a strong positive association. There's a strong positive correlation between passengers and promotional budget. There's a strong association between passengers and promotional budget. Now the client, from their business point of view, based on their knowledge or experience, they are going to give you their inputs. Imagine I'm your client. I'm giving you this input to you. Yes, your analysis is correct. Even in my 25 years of experience in this airline industry, I have observed that whenever we spike up promotional budget, we have seen a spike in passengers. You're absolutely right. Your analysis is right. Yes, there's a strong positive association between these two variables. I already am aware of it. Maybe next week, our plan is to spend around $500,000. Next week, we are planning to spend $500,000 on promotional budget. Next week, we are planning to spend around $500,000 or $500,000 on promotional budget. Can you predict how many passengers will be arriving if I am spending this much promotional budget? Are you getting what I'm trying to ask? Next week, the plan is to spend around $500,000, $500,000 in promotional budget. Can you predict the number of passengers in that case?
I think yes, we can, Venkat sir, but
Yes.
the correlation will not give that.
Correlation may not be able to predict.
Yeah.
First of all, is this a fair question or not? Is it somewhat related question to our analysis? I would say yes, somewhat very nearby to our analysis. But correlation coefficient, it cannot answer that question. Correlation coefficient is a very simple measure, very plain, simple. What it can do, given two variables X and Y, are they positively related? Yes, it can tell you. Are they negatively related? Correlation can tell you. Are they strongly related? Correlation can tell you. Are they weakly related? Correlation can tell you that. But given the value of one variable, can it predict the value of the other variable? Can it do that prediction? Sorry, the formula doesn't have the ability to predict based on the input. It cannot predict the target variable. We have to come up with some new methodology. So can I use correlation for prediction? Sorry, you cannot. So let's think about a solution to this. Imagine this is your data. You have X, you have Y here. Now, by looking at the scatter plot, what can you talk about this data? Is there a relationship between X and Y, or X and Y are not at all related? Looking at the scatter plot, what are your comments?
Related.
X and Y are very much related. When X is a smaller value, Y is a smaller value. As X is increasing, Y is also increasing, isn't it? X and Y are very much related to each other. Now, if I ask you this question, if the value of X is 30, if the value of X is 30, can you roughly give me the predicted value of Y?
40.
Roughly, at
20.
what number it
40.
will be?
40.
If the value of X is 30, roughly what is the predicted value of Y? Roughly around what number it will be? Everybody? It will be around 40. Is that a right answer? Is that the answer that you're thinking?
Yes.
Isn't it? 40 is the right answer. If the value of X is 30, what is the predicted value of Y? It will be around 40. Now, how come all of us came to 40 only? Everybody told 40, 40. That means we all of us are following a certain procedure to arrive at it. I want you to take one step back. I want you to go back one step and think about that procedure. What is the procedure that you have followed to predict the value of Y is 40? I think all of us have done this. You have imagined a line through this data. Yes or no? Once you imagine that line, you forgot about the data points. You don't care about the data points. After that, you started drawing X is 30. It hits it here. And then roughly it is 40. Is that the procedure that you have followed to come up with the number 40 as the predicted value?
Yes, sir.
Yes.
We have imagined a line that represents our data. Yes or no?
Yes, sir.
Once we imagined this line, you forgot about the data point. Tell me, once you imagine this line, almost we ignored the data points, isn't it? This is the line that goes through most of the points in our data. Do you agree?
Yes, sir.
This is the line that goes through most of the points in our data. And not only at 30, once you have this line, if I would have told you when X is 20, can you give me the predicted value? Can you give me that? If I would have told you when X is 15, can you give me the predicted value? Can you give me that?
Yes.
This is the line that gives us predicted value of Y. It gives us predicted value of Y at any given X. Yes or no? Not only 30, even if I would have told you 40, can you give me the predicted value? Of course you can. So that is the line that all of us have used to come to the predicted value. The line that you have imagined, that line is known as regression line. Regression line is the one that is used for prediction. Now, if you search for the definition of regression line in books and theory, this is what the definition of regression line. What is a regression line? A regression line is a line that represents our data. A regression line is a line that goes through most of the points in our data. A regression line is a line that gives us the predicted value of Y at any given value of X. This is the theoretical definition of regression line. But intuitively, maybe some of you are already aware of regression line. Some of you may be looking at the regression line for the first time, but intuitively, all of us, we do understand, we do use regression line for sure. So I've been saying that line. But in mathematics, you cannot call a line as line. If you're saying this is a line, you have to write the equation of that line. So what is the equation of the straight line? What is the equation of the straight line from our school days?
Y is equal to mx plus b.
Y equal to mx plus c. That is the equation of the straight line. Do we have the x data with us? Before drawing this graph, we can draw this graph using the x data. X is with us. Do we have the y data? Yes, y data with us. We just need to find m and c. Can you also recollect what m used to be known as? What c used to be known as? M, we used to call it as slope or coefficient of x. C, we used to call it as intercept or constant. So y equal to mx plus c is the regression line equation. But usually it is not written like that. Regression line equation is not written in the way that is written here. Y equal to beta naught plus beta 1 x. Is this same as this one? Just observe both of them. Are these two equations one and the same?
Yes, sir.
Sir.
In the place of C, I have replaced it what?
Beta naught. Beta naught.
Beta naught, which is known as intercept. In the place of M, I have replaced it with what?
Beta 1.
Beta 1, coefficient of x. So y equal to beta naught plus beta 1 x is the regression line equation. So next time when you see that, especially for those who are looking at this for the first time, can you identify this as a regression line next time when you see this? Y equal to beta naught plus beta 1 x. Now let's connect it to our case. Why did we start this whole thing? A client has asked us a question. So let's go back to the client's question. Do you remember the client question? Have you understood the client's question? Yes?
Yes, sir.
Now, based on this particular case that you were handling, can you go back to your regression line scenario and tell me what is your x variable name? What is your y variable name? First, tell me what is your x variable in your case? What is the x variable in your case?
Budget,
Promotional budget.
300 crore.
So x variable, what is the variable name?
Promotional budget.
Promotional budget.
Variable name is promotional budget, isn't it? That is a variable name x. Variable x is promotional budget. So you are giving promotional budget as input, and what are you predicting? What is your y variable? What is your target that you're predicting? What are you predicting?
Passengers.
You're predicting passengers.
And just
Your x variable name is promotional budget. Your y variable name is passengers. Have you understood this? In this case, x and y variables, how we have come up with this? What are you using for prediction? These are known as predictors or independent variables or input. And what are you predicting? They are known as target. I'm predicting passengers. My target is prediction of passengers. Do you have the historical data of promotional budget with you? Do you have the historical data of promotional budget with you?
Yes, sir.
Around
Yes, sir.
1.5 year data, do you have it? All the promotional budget for all those 1.5 years? Corresponding passengers data, do you have it? Do you have the passengers data? Whenever promotional budget is this much, these many passengers have come. Do you have that data also available
Yes,
with
sir.
you?
Yes, sir.
Yes, sir.
So you have promotional budget data, you have passengers data. So in this regression line, y equal to beta naught plus beta 1 x, x data, you have it. Y data, you have it. That means all that you need to find out to complete this regression line. What is that you need to find out to complete this regression line? You need to find out
Beta naught.
beta naught, which is known as intercept. Beta 1, which is known as coefficient of x. What is x here? In our case, x is coefficient of promotional budget. Once you find beta naught, beta 1, once you find beta naught, beta 1, your regression line is ready. So there is a mathematical procedure called OLS, ordinary least squares. This mathematical procedure tries different values of beta naught, different values of beta 1. Basically, to find the values of beta naught, beta 1, we use a mathematical procedure called OLS. What this OLS procedure internally will do is, it'll try different value of beta naught, different value of beta 1, because if I change the value of beta naught, beta 1, the line changes. Do you also agree that to that point? If I change the value of beta naught, beta 1, the actual line itself changes. This is y equal to some 50 plus 1.5x. This is y equal to some 22 plus 1.3x. This is y equal to some minus 80 plus 1.6x. Do you agree? If I change the value of beta naught, beta 1, the line itself gets changed.
Yes, sir.
So what this OLS procedure does is, it will try different values of beta naught, different values of beta 1. Finally, finalize that beta naught, beta 1 pair where our line goes through maximum points in the data, where our line has the least amount of error. So by minimizing the error, these beta naught, beta 1 are captured. So the exact theory behind it, maybe we will go a little later. Right now, we will take this OLS procedure. By using this OLS procedure, internally it will try different value. What we need to do is, we have to supply our X data, we have to supply our Y data. By supplying X and Y data to this OLS procedure, we will let that procedure to go through all its iterations, try different values of beta naught, try different values of beta 1 to give us the final optimal value of beta naught, beta 1. What is optimal value of beta naught, beta 1? Where your line goes through max to max points in the data, where you have the least amount of error. So how do you supply your data? How do you run this OLS procedure? What is the code behind it? You first call the package, import the package. My model is equal to package.ols formula equal to, until here it is syntax. Then you write y tilde x. Y is passengers, X is promotional budget. You have to tell Python that I'm using the target variable Y and my Y variable name is passengers. I'm using this variable X for the prediction. So my X variable name is promotional budget. Both Y and X are part of our data set or the data frame called air passengers data. Tilde is part of syntax. So by the end of this, Y equal to beta naught plus beta 1x, the skeleton equation will be formed. Once you say model.fit, different values of beta naught, different values of beta 1, they will be tried. The final optimal values of beta naught, beta 1 will be given to us. Everything will be stored in this fitted one function. The output will be a very lengthy output. In that, several metrics are mentioned. Some metrics are important, we will pay attention to them. Some metrics are not important or redundant, we can simply ignore them. But in this, definitely you will have beta naught, beta 1 mentioned. Beta naught in the place of intercept, you will get it. Beta 1 will be represented as coefficient of promotional budget. Both of them will be given under the section coefficients, or they are known as regression coefficients. So I want you to go back to your code file, execute this piece of code, go back to the code file, execute this particular piece of code, and then you will get the output. Browse through that output from top to bottom, browse through it, and find out what are the values of beta naught, beta 1, and give them in the chat window. What are the values of beta naught, beta 1? So when you browse through it from top to bottom, in this output table, you will get the values of beta naught, beta 1. So if we go back to the code file, if we try to execute this, in the output, in the second table, can you see them? Beta naught value 1259.6058. Beta 1 value coefficient of promotional budget, 0.0695. All of you found them, right? Beta naught, beta 1. Beta naught is 1259.6058. Beta 1 is 0.0695. All of you, have you found them? In the second table, you have these two values. We are now ready to finally write the regression line equation. What is the regression line equation? Y equal to beta naught plus beta 1 x. What is the y variable name? What is the y variable name?
Passengers.
Passengers is equal to, what is beta naught value? What is the beta naught value that we have got?
1259.16.
What is beta 1 value?
0.0695.
Into, what is the x variable name?
Promotional budget.
Now I now have the regression line with me. What is the whole point of building this regression line? Where did it all start? It all started with the question that, can I make a prediction of passengers given the promotional budget? Are you in a position to answer that question now? Given the promotional budget, let's say 500,000, $500,000, can I predict the passengers now with this regression line?
Yes, sir.
Yeah, go ahead, make a prediction. Tell me how many passengers are expected with a promotional budget of 500,000. How do you do that? You supply this here, multiply it with 0.0695, add 1259.6058, then you will get the predicted number of passengers. So give me that number. How many passengers are expected if 500,000 is the promotional budget? Around roughly 36,000 passengers are expected. Is that the number? 36,009 passengers are expected. Is that the number that all of you are getting? 36,000. So this is 9. So this is the input. This is the output. So something that takes input, this equation takes the input, gives us the output. That's why it is known as a model. It is also known as regression model. Since it is taking the input, giving us the output, that's why it's called regression model. Since it is giving predicted value as output, this is known as predictive model. It is also known as predictive model. It is taking the input and trying to give us the output, which is a predicted value, that is known as predictive model. It is also known as machine learning model. Regression, machine learning model. Regression is one of the basic machine learning model, one of the simplest form of the machine learning model. What is a machine learning model? Machine understands the patterns in the data. Machine understands the patterns in the data. it creates a mathematical equation out of those patterns. Mathematical equation will be created out of those patterns. We can use that mathematical equation to make the predictions. Machine understanding the patterns in the data, creating a mathematical equation. Using that equation, we can make predictions. This process is known as machine learning. Machine learning is not always about some machine is learning on its own. It's not the literal meaning that we should see. This is the meaning of machine learning. Sometimes the patterns are quite simple, where you can just use a simple regression line to solve this problem. The machine learning algorithm that we use this type of problem solving is regression model. Sometimes the patterns are quite complex. Sometimes maybe this is the image where we have to predict whether it's a tree, or in this image whether it is a car, in this image whether it is a person. Based on that, we have to build a model, and this model will predict whether it's a tree or a car or a person, and then this will be used in a self-driving car. And that will be a very complex machine learning model. This is also a machine learning model that is used in a self-driving car to predict what is the object that it is seeing. This is also a machine learning model where we are predicting the number of passengers based on the promotional budget. One of them is a very simple machine learning model. The other one is a very complex machine learning model. For a simple machine learning model, we are using regression algorithm. Later on, for a complex machine learning model, we'll be using artificial neural network, deep neural network, different type of advanced complex machine learning models. Even whatever we were discussing in large language models, where we are predicting the next item in the sequence, that is also a very advanced machine learning model. All these fields, machine learning, deep learning, AI, generative AI, data science, these are all interconnected. We cannot say that this is machine learning, this is not machine learning, this is generative AI, it has no connection to machine learning. We should not say like that. Data analytics, data mining, predictive modeling, machine learning, data science, data analytics, all these are interconnected. Are you with me, everyone?
Yes, sir.
Now I'll explain the theory behind what exactly that OLS is doing. We'll try to visualize that. But before getting there, let us take a couple of questions. Yeah, please go ahead. All right. It's clear until here. So let us try to understand, like here, we have taken a mathematical procedure for granted. We thought that, okay, if I give the data, automatically that mathematical procedure called ordinary least squares, it will actually go through various iterations. It will find the beta naught and beta 1. It will give me finally. Do we get to see this mathematical procedure? No. Do we get to modify this mathematical procedure? No. Can you do anything with it? Is there anything under your control? No, nothing. You supply the data, this mathematical procedure will work and give you the result. That is the reason why we did not pay attention to this, because there is nothing that we can do about this. So mathematically, somehow, this beta naught 1, beta naught and beta 1 values are calculated. But if we want to understand the theory behind that mathematical calculation, so what exactly is happening behind the scenes? If you take your data points as these are your data points. Imagine this is your regression line, y equal to beta naught plus beta 1x. As of now, it's an abstract y equal to beta naught plus beta 1x. I don't know what is beta naught, what is beta 1. Now take point xi. If you take point xi here, let's say this is point A, this is point B, this is point C. At xi, what is the actual value of y? At this point x, what is the actual value of y? Is it A or B or C? The
B.
actual value of y is what? At point x. So this is the data point. For this data point, for this x, what is the actual value of y?
C.
C. This is y actual. Do you agree? Now at the same point, what is the predicted value of y?
B.
B.
if you take this as a regression line, regression is going to predict that for this point, this is a predicted value of y. Be careful, some of the videos are on, okay? So at this particular point, what is the predicted value of y? It is b. This is the y predicted. This is y actual. This is y predicted. Are you with me, everyone? Because regression is going to make this as prediction. But this is not the right prediction. Regression is making some error. Can I call this is the amount of error this particular regression line is making at this particular point? At this particular point, this is the error made by the regression line.
Yes.
Similarly, at this point, this is the error made by the regression line. Actually is here, prediction is here, this is the error. At every point, my regression is making some error. Do you agree or not?
Yes, sir.
These are all the errors made by the regression line. Some errors are positive, some errors are negative, but error is an error. It's not that if the predicted value is higher than actual value, will I be happy? There's nothing like that. Error is an error. Predicted should match the actual value. So this is also an error. This is also an error. There are some positive errors. There are some negative errors. We have to minimize all those errors. But we cannot simply take the summation of all those errors, because some errors are positive, some errors are negative. Instead of minimizing the direct sum of errors, what we will do? Minimize the sum of
Right.
squares of errors. If you try to minimize the sum of squares of errors, then you will have the best regression line. So you want to minimize sum of squares of errors. What is an error? Y actual minus y predicted. Usually y actual is denoted by y predicted is denoted by y hat. Y actual minus y predicted whole square, that need to be minimized. Now what I want to minimize is y actual minus what is y predicted? Beta naught plus beta 1 x. This function need to be minimized. This is called cost function or the error function, or also known as cost function. We need to find such beta naught beta 1 that will minimize this whole function. We need to find such beta naught beta 1 that will minimize this cost function, that will minimize this error function. Now, how do you find the minimum value of a function y equal to f of x? How do you find the minimize? Like what value of x will minimize this whole function? If you go back to school days, what we used to do? We have to take dy by dx is equal to 0. D square y by dx square is greater than or equal to 0. So we used to do all these calculations. This is known as derivative. You remember derivatives? In multi-dimensional space, this is known as gradient. So what we try to do is we'll try to find such beta naught, such beta 1 that will minimize this whole gradient. So we will try to move in the direction where the error is reducing. So the error function looks like this. So this is your beta naught x value. This is your beta 1 y value. As x and y, if you choose here, the error is high. If you choose here, error is high. So you move in that direction. You start, this is called gradient. On that gradient function, you're getting into gradient descent. That means you are moving in that direction where the error is descending or reducing. When x is 75, that means beta naught is 75. Beta 1 is 85. What is the error? 7000. When x is 30, when you move x and when you move y, what is the error? 2000. From 7000, we came to 2000. Like that, if you further move, when x is 25, y is 5, error is now 131. There are places where error can be 100,000 also. Let's say if these are all the data points, if my line is here, the error will be huge, isn't it? If my line is here, it will be even huge. So I want to move much closer. I want to have such beta naught, such beta 1 that will be having the minimum error. May not be zero error, because not all points may pass through that line, but minimum to minimum error. When x is 25, y is 10, maybe this is the least error that I could get. So what's happening behind the scenes is we are looking at the error function, and error function is a function of your beta naught beta 1. We are trying such beta naught, such beta 1, which will minimize this error. This whole procedure is known as gradient descent. Usually we don't talk about it because this is not in our hand. We don't really have anything to change in it. We pass on our data of x and y. Let this gradient descent happen in the backend. We used to get the value of beta naught and beta 1. Maybe just for the sake of visualization, I'll try to show you what is happening. I created a simulation that will give you an idea how this gradient descent is working in the backend. So all this visualization, etc., I have kept it in a certain file on GitHub. So what we need to do is we need to get that file. I have stored that as a cost visualization. That means cost means error visualization package.py. Then it's almost like a package. We can import certain functions. So I have written certain modules in that. We can get those modules. But the focus is not on the code of visualization here. The focus is to get an idea on what happens when error being minimized, what happens, how these beta naught, beta 1 are calculated. Usually we don't get into all this. Generally our focus is on getting the beta naught, beta 1 values and to build a model to make the predictions. But here we want to get an idea just to see what is happening behind the scenes. So if you directly build the model, I'm getting intercept value as 25, coefficient value as 10. Beta naught is 25, beta 1 is 10. R square value is very good. But anyway, beta naught is 25, beta 1 is 10. Now, how these values are arrived? 25 and 10, we did not get them in one shot. This is the whole error function. So initially maybe X here means beta naught. X is beta naught, Y is beta 1. So initially minus 105, minus 45. Can I try it? Yes. But what is the error value? Z is the error value. Is that a minimal error? No, huge error. So if you try to see it, if I change the value of X, change the value of Y. When X is 170, Y is 155. What is the error value? X means beta naught. When beta naught is 170, beta 1 is 155. The error value is 39,000. If I go little here, see, as I'm going here, the error is reducing. When X is 90, Y is 140. What is the error value? It is somewhere around 19,000. So let's zoom in. Let's go a little bit in there. When X is 80, when Y is 120, what is the error value? 14,000. Let us zoom in further. This is the error space that I am moving in. When X is 70, Y is 45. What is the error value right now?
2000.
2000. When X means beta naught. When beta naught is 60, beta 1 is 35. What is the error value? 1000. That means, like, shall I go further from here? Shall I go even lower? Gradient descent. Shall I move in the direction where my error is reducing? I have to go a little deeper, isn't it? Are you with me?
Yes, sir.
So I will go a little deeper. Now when X is 55, Y is 25, what is the error value? X is beta naught, Y is beta 1. It is 628. Shall I go far away from this? Shall I go into it? So it is called gradient descent. This function that you see is a gradient function. You get into that direction where your error is reducing. So slightly I will go. X is 50, Y is 45, 453. X is 50, Y is 20. X is 45, Y is 15. Can you see the error is reducing here? All of you? So that is what happens in the backend. Usually this visualization and so on is not needed, and it's not possible for multi-dimensions. When you have only a very simple regression X versus Y, then it is possible. But what if you have beta naught, beta 1, beta 3, then it is impossible to draw this. That is why people just take this whole theory for granted. But at least to get an idea, I have created this visual. Have you got a hang of the theory? What is working behind the scenes to give that final value to us? How these beta naught, beta 1 are calculated? Make sense?
Yes, sir.
Yeah.
Yes.
But it doesn't really matter. Even if we don't get that theory, it's fine. All that we need to do is supply that data, let that OLS do all those iterations, finally give us the value of beta naught and beta 1, which it gives. And then using beta naught, beta 1, we can create a mathematical equation, which we will indeed use it for predicting our target variable. Any quick questions before I move on to the next subtopic? Is it clear until here, all of you?
Yeah.
Yep. Now, look at this scenario. Here, we predicted the target variable Y using X. What is X? Promotional budget. What is Y? Number of passengers. Let us say this is Y, this is X. There is another data scientist who wants to predict the number of passengers only, but not by using promotional budget. No, but by using inter-metro flight ratio. Is there any rule that we have to use promotional budget only for the prediction of passengers? Has anyone set that rule? No.
No.
Do I have information about inter-metro flight ratio?
Hmm.
Do we have data around inter-metro flight ratio? We
Yes,
do
we
have
have.
the data, isn't it? So can I use inter-metro flight ratio for prediction of Y? You can. Let this be model M1, which is using promotional budget for the prediction of passengers. Let this be model M2, which is using variable X2 for the prediction of passengers. Now, M1 model predicted that, okay, next week the passengers will be 36,000. If M2 model also predicts that 36,000 will be the passengers, there is no problem. But what if M2 predicts 45,000 passengers are expected? What if M2 predicts that, no, 15,000 passengers are expected? What if this model predicts a much higher than what the previous model has predicted, a much lower than what the previous model has predicted? What if this happens? Which model I should take seriously? Shall I take this prediction as serious value, or shall I take this prediction as serious value? Which model I should believe? So that is why we need to be careful. Model building is one job, I agree. But model building must be always followed by model validation. You must always tell how good is your model. Model building must be followed by model validation. You have built a regression line, I agree, nice. But you must always tell how good is your regression model, how accurate are your predictions. So here we have a scenario where model M1 is predicting passengers, model M2 is also predicting passengers. But which model predictions I should take seriously when I compare these two models? Which model prediction I should take seriously? That is a question that arises. So here is how you can answer this question. Take your data. Take variable X1, which is promotional budget. Your target variable Y is passengers. Let's call that as actual value of passengers. So you have the promotional budget data with you. Do you have it? Do you have the passengers data with you? Do you have it? So supply this promotional budget to model M1. You will get the Y predicted values. Yes or no? By supplying the values of X to the model, can you get the predicted values? Earlier you have supplied 500,000. Have you got the predicted value? Do you know how to get the predicted values from the regression model? By supplying the values of X, we'll get the Y predicted values. Make sense or not? Similarly, you go back to data once again, get X2 variable, inter-metro flight ratio. Y actuals will remain the same anyway. Supply the values of X2 to model M2. Model M2 will give you the predictions. These are the predicted values by model M2. These are the predictions made by model M2. These are the predictions made by model M1. Imagine this is the result. These are all the predictions made by model M1. These are all the predictions made by M2. If I tell you, these are the two tables this model M1 gave, this is the table, model M2 gave this table. And if I ask you to pick one out of these two tables, which model do you think is doing a good job? Is it model M1 that is doing a good job, or is it model M2 that is doing a good job here? Is it model M1 or is it model M2 that is doing a good job here? If you had to pick one out of these two models, which model would you pick?
I think M1 because
M1, sir.
actual and
Which
prediction having
model?
the
M1.
less
Sir,
values.
none. We cannot choose anyone from them.
M1, M2, or none. So let us think about it. If let's say at a particular point, 40,000 is the actual value. If the model is damn good, if the model is really robust, if it is a good model, if 40,000 is the actual value, what is the predicted value that you expect from the model? If 40,000 is the actual value, what is the predicted value that you expect from the model?
Near to 40K.
Near to 40K. Exactly 40K would be best, but near to 40K is expected. If the predicted value is 39,000, can I say there is 1,000 error here?
Yes.
There is some error here. There's some error here. Here there is no error. There's some error here. Here there is no error. There's some error here. Like that, M1 is making some errors. M2, is it making some errors? M2 is also making some errors. Comparatively, now compare M1 and M2. Overall, which model is making lesser error overall?
M1.
M1 is making less error. So if I ask you to pick one out of these two, which one is your first preference? The one that has a lesser error. Because if actual value is 27,000, predicted value is 26,000, error is 1,000. Actual value is 30,000, predicted value is 31,000, error is minus 1,000. So sometimes the error is positive, sometimes the error is negative. Nonetheless, an error is error. Actual should be matching prediction, then only it is correct prediction. Otherwise, it is an error whether you are predicting a slightly higher value, whether you are predicting it has a slightly lower value. Do you agree? Error is error. Now for a good model, what should be this overall error? As minimum as possible. To get an idea on the overall error made by a model, can I take the sum of all the errors? Is that a good idea to consider summation of the errors? The sum function has some issue here. What is the issue? If you directly take the summation of all the errors, what will happen? Some
Plus
errors are
minus
positive,
25. Yeah.
some errors are positive, some errors are negative. They may cancel out. Overall, it may looks like no error. That means minus 1,000 is an error, plus 1,000 is an error. But if they cancel out, it looks like model has made no error. Is that really true? Model has made minus 1,000 error, plus 1,000 error. It's not like no error. So instead of taking summation of errors, what is a good idea here if you have plus minus kind of issue to get an idea on the overall error? Instead of taking the summation of errors, you take the squares of them. Instead of finding out sum of errors, you find the sum of squares of errors. It is known as SSE term. So for a good model, what should be sum of squares of errors value for a good model? For a good model, what should be sum of squares of error value?
Should be
As minimum as possible, very much near to 0. Now, if you take, these are the Y regression predicted values. If you take the squares of all these regression predictions, then take the summation. That is known as sum of squares of regression predictions. This is denoted by SSR. This is denoted by SSE. If you take the squares of these values, that is known as sum of squares of total, SST. There's some theory which proves that sum of squares of total is equal to sum of squares of regression plus sum of squares of error. SST is equal to SSR plus SSE. Now, if you look at this equation, we already know that SSE should be near to 0. If I ask you this way, what should be SSR value for a good model? SSE should be near to 0. What should be SSR value for a good model?
Edge close to SST.
as close to SST as possible. That means I mean to say the prediction and actual should be almost close to each other. What should be SSR divided by SST value?
R square.
1.
It should be
Near to
if
1.
R square, if SSR should be equal to SST, SSR by SST should be near to 1. This SSR by SST is named as R squared. And for a good model, what should be that R squared value? That should be near to 1. Let's go through it once again. So we know that sum of squares of error should be near to 0 for a good model. And this is the theory which proves that sum of squares of total equal to sum of squares of error plus sum of squares of regression. This must be near to 0. That means this must be near to sum of squares of total. Sum of squares of regression divided by sum of squares of total. That should be near to 1. That sum of squares of regression plus sum of squares of divided by sum of squares of total is known as R squared value. So for a good model, what should be R squared value for a good model? R squared
Near
value
to
should
1.
be
Near to 1.
near to 1. The usual industry benchmark is when you are building a model, yes, R square should be near to 1. But when you are working on any of the model building techniques, when you are working on practical data sets, you expect at least I have a decent model when I have R squared value above 80%. If you have R square above 80%, at least I can say that I have a decent model with me. Minimum R square that you should always try for is at least 80%. That's the general industry standard. Then only I will say my predictions that I'm giving are kind of reliable. At least you can trust my predictions that are coming out of my model. R square value should be near to 1. We have already built one model. We tried predicting passengers using promotional budget. You remember that? Model M1, we have already built that. We also got the predictions. But can I trust your predictions now? Whether it is a good prediction, bad prediction, whether it's a good model or bad model, I cannot really trust unless you tell me how good is your model. Can you go back to the code file? Can you go back to the output of this model? Check whether this is a good model or not. Can I trust the predictions given by this model? Check in the output window what is R square value. Based on the R square value, tell me, is that a good model or not? Can we really trust the predictions given by this model? Is this a good model or not? What is the R squared value of this model? What is the R squared value? Let's go back to the code file. Let's go to the place where we have executed this. This is the model that I'm talking about. Promotional budget versus passengers. In this model, what is R square value?
0.93.
0.93. 0.93. What is the general industry standard? When do you say you have a good model with you? A decent model? Above 80%. Right now, the R square value is 93%. Is it a good model? Can I trust the predictions given by this model?
Yes, sir.
Yes?
Yes,
Good
sir.
model? Yeah. We can take these predictions seriously. Now I want to challenge that model. I want to build another model which is also predicting passengers, but by using another variable called intermetro flight ratio. If I want to predict passengers by using another variable called intermetro flight ratio, if I build this model and I am comparing model M1 versus model M2, between M1 and M2, which model I should choose and why? If I have two models, model M1 and model M2, build model M2 as well and compare them and tell me which model I should choose and why.
We should choose the model 1 because R square value for model 2 is 0.24 only, which is
The R
below.
square value of model 2 is 0.24, which is quite less compared to R square value of model M1. So I would, if given a chance, we would like to go with model M1. Does that mean when you are getting the predicted values from model M2, Are you going to get an error message in Python saying the R-square value is very less, I cannot give you the predicted values? Are you going to get that error message in Python?
No, sir.
No.
No, the predictions will be made. You will get the predictions. But what's the problem with those predictions?
Error.
They are not accurate, erroneous. So any model will give you predicted values. Any variable will give you predicted values. You can use any variable for building a model, but the model's real respect, the model's real value lies in where? What is that which is very important for us? As soon as you build the model, you must always look at,
Validate.
you have to validate the model. Model building, model validation. I would say model validation is as important as model building. Do you agree with that? Because you have n number of ways to build the model, but how good is that model decides whether I should use this model or not in future. So it should come naturally to you. Immediately after model building, you must always think of a way to validate how good is this model. Model validation is as important as model building. Make sense?
Yes, sir.
Yes.
Yes, sir.
Before I proceed to the next subtopic, let's have some questions and clarifications.
Venkat sir, that there was another term called adjusted R square. What is your interpretation? If you could elaborate.
So adjusted R square is a kind of variation of R square. Using the R square formula, by adding some penalty factor, adjusted R square is created. So adjusted R square is used if there are too many features or if there are too many variables. Actually, adjusted R square comes into the picture only when there are multiple variables. For a single variable, adjusted R square doesn't make any sense. There is no meaning of that. But if there are too many variables, then sometimes R square seems to be really high, which it should not be. So adjusted R square will give us an idea on what is the true R square. But there is a way to get rid of the too many variables. If the variable is not impactful, then we will anyway drop it. So even without the adjusted R square, you should be able to manage it. Okay. It is just a variation of the R square value. All right. Now, we have predicted the passengers using promotional budget in isolation. That means when we were building this model, we never considered any other variable. We predicted the passengers using intermetro flight ratio, That was also an isolated model. That means we never considered any other variable while predicting passengers apart from intermetro flight ratio. But honestly, in reality, it is passengers along with intermetro flight ratio, along with service quality score, along with X4, along with X5, along with X6, along with all these K features will impact the target variable Y. Do you agree? The number of passengers are not just impacted by one feature at a time. Some total effect of all these features will result in the number of passengers. It's a certain promotional budget along with intermetro flight ratio, along with service quality score, along with all these features put together. All of them should be used for the prediction of target variable in one go. Isn't that true? Real world is multivariate. One variable depends on multiple factors. If I want to predict whether a customer is a defaulter or non-defaulter, whether he's going to pay back the loan or not, is it just the income that I use? I will use income, number of loans, number of late payments, monthly utilization, number of dependents, etc., number of existing credit cards. We will use multiple features for the prediction of one target. What is it? Whether the customer is going to be a good customer or a bad customer. Do you agree the real world is multivariate? Multiple variables are used for the prediction of target variable. Whatever we have seen here is X versus Y. This is called simple regression. But in reality, it is X1, X2, X3, and so on, Xk versus Y. This is known as multiple regression. Multiple features, all these are known as features. Multiple features are used for the prediction of the target variable Y. Earlier, the model was X versus Y. It looks somewhat like this. Now, if it is X1, there is another dimension X2. Then we will be building a plane. Some points are above it, some points are below it. We are adjusting this plane. This is Y equal to beta naught plus beta 1 X1 plus beta 2 X2. This is the regression line if you have two features. This is known as multiple regression line. If you have multiple dimensions, the extended version of regression line would be, this is the extended version of regression line. Y equal to beta naught plus beta 1 X1 plus beta 2 X2 plus and so on beta k xk, where you have k features. This is how the real world models appear, isn't it? Multiple features are used in the prediction of the target variable Y. Maybe if you are using just one feature, you may get very less R square. By using multiple features, we can push the R square slightly higher. Given that all these features are kind of impactful, they are really having some information about Y, which we can use it for prediction. So this is called multiple regression, and reality, we will be building multiple regression models. Now, what is the syntax difference? Earlier, we have imported the package, import the package. My model is equal to, earlier we wrote Y tilde X only. Now you write Y tilde X1 plus X2 plus X3 and so on plus Xk. This is not a literal summation of the values. It is a way to tell Python that use this as the Y variable. This is feature 1, this is feature 2, feature 3, and so on, feature k. And all of them are found in this data set. And then once you say model.fit, automatically beta naught, beta 1, beta 2, beta 3, and so on, beta k features will be calculated. Beta k, like for each of the feature, these coefficient values will be calculated. What is the advantage of it? You will have slightly higher R square because you are using multiple features. Usually one feature may not have the ability to explain the complete information about the target. You use multiple features for explaining the target variable. That is known as multiple regression. In reality, we will be building multiple regression model usually. Go back to your code file, build this multiple regression model, and tell me your observations from the output. Build the multiple regression model. Tell me what are your observations from this output.
R square is 0.951.
As soon as I say, what are your observations from the output? As soon as we go to output, what is that one most important metric that we immediately should check always? I'll go to the output and I'll check the value of
R square.
R square. R square is such an important measure in our whole output, isn't it? In our whole discussion. Do you really pay attention to a model where R square is 0.51? It's quite a small value of R square, isn't it? So R square value should be above 80%. For this model, R square is around 95%. What does that indicate? Is it a good model? Can I trust the predictions given by this model?
Yes, sir.
Yeah.
Yes, this is a good model. So that is the story of regression. This much of regression we must know before we proceed. But in reality, regression is much larger than this. Usually I take machine learning sessions. During those sessions, regression goes much lengthier than this. There are certain other measures like adjusted R square, like multicollinearity, like p-value. All of that we discuss, and then we write down all the steps in building the regression model, and then we do a case study on regression. All of that we generally tend to do But here our focus is on generative AI. There's no point in going back to machine learning again, spending all the time on it. But if you really want to know a bit more about regression, again, you can always reach back to Sajid, get access to some other machine learning sessions and go through regression. But this particular one, this much you must know. This is like bare minimal essential that you must know. You must be very confident in this. Are you confident in this, everyone?
Yeah.
Yeah.
Yes, sir.
Let's take a quick break. Right after the break, we will get into the next subtopic of discussion.